say contact, please. That face mask, you see that face mask?
Okay, so we're gonna start something new today. Stuff you probably haven't seen very much of, but it's right down intermediate fluids. All right, so give me whatever you had. What did I say by tomorrow?
Yeah.
For the homework or test. Did I say tomorrow?
Yes.
Test. Yes.
MATLAB homework and.
Yes, you gotta probably, most people probably need to work on MATLAB. The CFD, don't worry about that. That can wait. I'll give you another couple
On
of
that
weeks.
one or so.
And I will post a new homework on this stuff. We're gonna go through stuff today. Next class, we're gonna go through a whole bunch more problems. Week 5, 4, we got, which is starting Thursday, we'll do more problems. And it looks like week 5 will be a work day, and then we'll review, and then we'll have a class, a testing class. Okay? And I'll make sure to post a whole bunch of practice problems. It'll cover this, and it'll cover the kinematics in homework 1. Okay, but I'll go through a whole bunch of different problems.
Not that.
Okay? And I'll probably post a practice test that you can look at. So you should be well prepared for that test. I actually, I'm starting this like 4 weeks earlier because I'm throwing away, kind of got rid of some of the stuff that's review that I know the students really didn't need again. So, because I want to get to more of the cool stuff like shock waves and go up to Clarkson and do that lab. So I think we're on a good way right now. So.
Can we bully the Clarkson kids,
No.
please?
All right, so today we're going to analyze linear momentum on a control volume and then understand how we can develop steps to solve these problems, okay? So, for example, these problems involve if you have a big pipe or whatever, small pipes, doesn't matter, water going through it, how much force do you need to hold that pipe stationary, okay? Or as simple as a fan that you have in your house, how big of a base do you need so it doesn't fall over? One of your homework problems is going to be that. It's going to be plot the wind speed as a function of that distance so you can get an idea of what that trend is, okay? So we'll get into all that stuff. So let's do a sketch. And I think I can move it this way. We're going to draw a spigot. Water spigot. What's that?
So straight.
I know, I'm trying. So the black things are screws. Bolts. How do you think about it?
squared.
It's gonna be square. There. It's a little better.
A little easier, I guess.
So, while finishing this, this is a water spigot on the outside of your house. Every time I turn mine on, I always think about this, okay? You got bolts holding it in. When you turn this on, water's gonna shoot right out, right?
Depends.
We can figure out, using this linear momentum analysis, okay? Throw some water in here. How to size the bolt, what forces you need, right? So as long as you understand what forces are required to hold this in here, then you can go and size the bolts, right? The machine is not. Okay, so you can see how we need to do this, and then we use the other class, and then finally we can say, okay, here's our completed design. Okay? So based on this, what we do is we make a control volume. So the control volume is like your system boundary in thermal. Remember that? Is that green too much? So we capture the whole thing on the outside. All right? That dotted section all the way around here is what we call our control volume. Anybody want to guess what we do on this control volume?
Calculate.
Well, in thermal, when we did a boundary, would be labeled in out of energies. Here, we're doing control volume, we're dealing with forces, we need to do forces. Okay? So give me one force acting on that control volume.
Force of the water?
Force of the water, yes. And that goes upward?
Yes. Sure.
Downward, you mean?
Sure. It goes off the pretty.
WH2O. All right. What else? What other weight do we have?
The mass of the watershed itself.
You mean the weight of that? Yep.
Yeah.
And I'm just putting an arbitrary place. Weight of the faucet or the spigot. Yep. Okay. What else do we have?
Could you do the force on the bolts?
Yes. You are correct. Now, we don't know what directions they are, but we'll figure out in our analysis, right? We'll call them resultant forces. Okay. What else we got? That's what the weight forces are. So we have weight, we have reactions. As soon as this water hits this, pressure times what? Gives you force. Area. So the area of it coming out, we'll call P2 times A2. So thermal, remember doing that to find the pressure inside the system boundary? And then we also have this right here, right? This pressure times the area. So this is atmospheric pressure, and that's the pressure inside the waters. So, this is how we do it. We pick our system, we pick a boundary, this dotted section, which is our control volume, and we look at all the forces acting on it. Okay? Water comes what?
What do you mean?
In here,
Oh,
yeah, that's what I meant, sorry, at 1, and then shoots out
I took.
here. That water force, we're going to end up writing It's basically, in order to figure out these forces, there's m dot times the velocity. But we're gonna wait, we're not gonna write those in there. We're just gonna look at these forces here. And then we'll set them equal to something, okay? So, if this water shoots out this way, which way does this spigot wanna go? Up, okay? All right? And then if this shoots this way, kind of want to push it back that way, okay? So, good.
Do we deflect that in our?
What's that?
Do we deflect the force that would?
No, those two red ones we're going to include.
Okay.
But you know how we always write, I'm going to show you this in a second, but we always do this in Newton's second law, but we never really write the force of inertia here. Okay, a lot of the times, that's kind of where these forces are going to be implied, inside there. Okay, so as long as you label in and out, you're good. So this is actually section 2. This is good. Now, you have forces, but like if you look at a fire hydrant bolted into the ground, okay, or even this, they also create moments, right? So sometimes you can figure out the moment. Figure out, okay, is the moment too large and you need to resize something. All right, so what is the equation? How do we get it? Well, let's start right with Newton's second law. Questions so far? I'm going to show you where the fundamental equation we're going to get to, but it's good to know where it comes from. I'm going to rewrite acceleration in terms of dv dt. And I'm going to bring in the mass into the parenthesis. And what is m times v called in dynamics? Students in dynamics
So mass times.
might not know it. The students have taken it, they know it. Remember when we had two trains coming in at each other?
Right.
We did conservation of momentum. So this mass times velocity is called linear momentum, okay? So let's look at a nozzle and how we can split that equation up a little bit more.
So this is a completely separate one?
Yeah, this is just to show you something. I'm going to write this and we'll talk about it. So here's this nozzle. Here's our dotted lines. Coming in, our control volume, which is labeled CV, that's what we call it, is you have all that momentum coming in. All right? Out of this, you have momentum going out. And then you have change of momentum inside your control volume. All right? The easier way to look at this is, what is dm over dt? Remember? What's dm dt? The change in mass over change in time? Fluids and thermal? What do we call it? M dot. So it's the mass flow rate times velocity coming in, which is a force. And then you have stuff going out, which is also another force. And then that is basically your mass m dot times velocity of the controller. Okay? So you see how these are momentum, but they could be related to forces. So the way we write this, for your case, is this way. So here, we have the sum of the forces, and those forces were all the forces we labeled on that spigot beforehand, okay? That equals the mass times acceleration of your control volume plus your mass flow rate times velocities out minus mass flow rate times velocities coming in. Why do you think there's summations on these two? Because you could have multiple things coming in. Like if you have a fire hydrant, you could have like 3 or 4 different things coming out. And you might not have anything coming in except for the bottom, so 1. But you could have multiple things coming out. Now, in a fire hydrant, this is is it moving? It's not moving, so that would be gone in a fire hydrant. But if you have like a car that's shooting water out the back or whatever, that's accelerating, right? It could accelerate. You would include that term.
Like a bottle
rocket. Yeah. Or in outer space, it starts moving, it gets accelerating. But if it's moving, if it's stationary, it's gone. If it's moving at constant velocity, that term's gone. Okay, we'll do a lot of them where that's gone away. Okay.
jet ski.
Jet ski. Yep. The jet ski, if it's accelerating, then yes, you have to include it. A lot of times when you'll do analysis, we'll do one of those problems exactly, but it's moving at constant speed. But the water in the bottom comes in at an angle, and then shoots out at a different angle. And you just have to figure those. That's why you have vectors here. Okay. The vectors indicate X, Y, and Z directions. Good, does that make sense? So, if you look, these again, all the forces that we had in the spigot, and we labeled what's coming in and going out. Then we can write, okay, that's the flow rate coming in times that velocity in that direction. Now, let me show you why it's out minus in. So let's look at the little car, the little dragster car. Here's the road. car's going left. It's pretty aerodynamic. And it's moving at constant speed. We did the forces acting along the X direction. Give me one force.
X.
Drag.
Drag. In which way is that acting?
Left.
The opposite direction. This way.
Yep.
Or right this way.
And then what else? This thing is shooting out the back, so it creates a thrust, just like airplane engines. But it propels it that way. All right? But if you look, these gases are actually doing what? Going to the right, but it creates a positive thrust. Okay? We'll keep going, I'll show you, it'll make more sense. So if we do what we just did with that equation here, then we have drag force, which is the only really external force, times m dot out times negative v out. Minus FD plus T. So write that, we'll talk about what I did. So what I did here is, this is the equation I just showed you. In order to do this, this thrust would come off, that force. And you do a control volume, and you look, okay, there's only one force, which is negative drag. Then you look at what's going in and out of that control volume in terms of the fluid. There's nothing coming in, okay? Well, you have, because it's moving that way, you identify that as positive. That's why you have negative V out of this fluid. So here you have negative drag equals m dot out times negative V out. That in turns is really a thrust. And it's negative. When you bring it over to the side, it becomes positive. So this is what we get if we just did a free body diagram. If we did a control method, we start with this, with a dotted line and label what's going in and out. See how we can use this now to figure out really Newton's second law? Does that make sense? And that's why it's out minus in, because of our free body diagram that we would actually do, because thrust is going to the right or left. Okay. So always remember this. So in your homework problems, you're going to start with that. Okay? Sometimes you'll use this one. So box that one, and I'll show you this one. So we include these beta terms in here. If we don't assume that the velocity coming out or going in is uniform, okay? It could change depending on the location in the pipe. A lot of the times, the problems will give that to you, so you could just throw it in there. Yes?
Should there be a vector on top of the?
Yes, it should be, yes. Yep. Thank you. Almost there. Do practice problems. Questions so far? Okay, the last thing to point out, to understand the methods for this, is go back up to the spigot.
I didn't get the very last line
Oh,
on that.
okay, that's all right. The black one here?
Sorry. Yep.
Okay.
All right, we're good.
Good now?
Yep.
Go back up to the spigot. What do you think we want to use for pressures here and here?
For P1?
P1 and P2. What type of pressures do we want to use?
Inside the system.
Yeah. How do we make this problem easier? How do we get rid of P2?
Safety net.
Can't do that.
Close up the
Can't do that.
That's terrible.
Okay, then you would just need to figure out the weights and figure that out. No? Which one's going to be higher, P2 or P1? P1 should be higher, right? It's shooting out. How do I get rid of this? Use gauge pressure, right? Because if this is gauge, what is this? Zero. Okay, that's how we get rid of it. Okay? So anytime you do these, always use gauge pressure. And anytime it's atmospheric, it's zero. So
How is that though?
it's just because gauge is just, because it doesn't matter for these, if you scale the pressures, it doesn't matter. You can add or subtract anything to the pressures. You make it absolute or gauge, and it's fine. Okay, ready for a practice problem? Okay, let's do this. That is not far. Okay, we're going to look at what they do is called a thrust stand.
What's that one?
What's that?
What's that thing called?
This is going to be, there's an engine mounted on, it's basically going to measure thrust. There. And I guess we can open it, sure. So I mount this engine on a stand. And they actually have a whole bunch of sensors everywhere, right? Measuring temperature, pressures. They even have a force balance on here to measure the force that's generated from it. But to size it initially, right, and understand how it's going to work and stuff, we do these analyses to get an idea, right? Because if you build this engine, and then you only have certain sensors that will work in certain ranges, you got to build it, or you got to buy those right sensors. So, first thing you need to do is make a control volume. They draw right over the system. And I'm going to do some givens here for you. But we have E1, A1 here. P2, A2 here. Oh, and let's label, this is coming in, out. And let's write some givens for you. V1 in the x direction is 200 meters per second. V2x, 500 per second. V1 is 1 meter squared. It's down just a tad. They actually found that the pressure at 1 is 78.5 kilopascals. Temperature is 268 K, and this is actually atmospheric again. They're sucking the air in at 1, pretty much. Creates a low pressure from the turbines. And I missed one force, which is,
The weight of the engine?
we don't need to worry about that. So we're only looking for thrust. So we only need to worry about the x direction. Okay? But we're going to assume it's only moving in this direction. Alright? So we have pressure forces, we have thrust. And that's what we're going to find. We got air going through this engine, and it's spinning inside here, creating a low pressure up front, spits out the atmospheric pressure. Assumptions. Give me some assumptions. What do you think?
Is it uniform view? No, wait, no, it's not. So it's non-uniform.
Yeah, it's uniform. Well, uniform in terms of where the area is.
Okay.
So it's all, we're going to assume it's all 200 here and all 500 here. Okay? Yep. So that's good. So you could assume beta is equal to 1. Sure, we can write that down. All right. What other assumptions? Remember how I had derivatives when I looked at the nozzle, then I went to mass flow rate? That means it's steady state. Okay, there's no rate, there's no, velocities are always going to be the same at those locations all the time, so it's steady state. And then the last one is, it's air. In thermodynamics, what can we assume?
Is it incompressible?
Constant pressure.
No, because we have two different pressures.
Yeah, that's right.
It's not incompressible. It's compressible, so what equation can we use?
What was that one?
Give me the equation we use. Remember the equation?
No.
P equals,
Rho V.
no?
Rho CP.
No? Oh, you're getting warmer.
CH. There's two C's, wasn't there? I don't know.
No.
There's 3 letters.
Rho C.
Rho, blank,
Rho EV.
no. That's mass flow rate. Okay. P equals rho, make bank.
Rho.
CP delta T.
No, that's internal energy change for what?
That's the one I was going to say.
CP, you said CV delta T?
CP.
Plus CP delta T, that's delta H, that's enthalpy. Okay, that's good though. There's enthalpies going on here. Actually, we're going to use the ideal gas. No, P, we don't write it, P equals rho RT. Well, we're going to write that later, so Don't write that in your notes. I don't want that in the assumption there. I just want ideal gas. Perfect gas, remember that? You remember the compressibility factor, if it was not ideal? E equals rho r T, but you had to include the Z on the right. Remember that?
That chart's in the back too.
The charts are in the back, yeah, ringing the bells. So, here is there one now?
Got it.
Yeah, you're good there. Anybody else? Alyssa, you'll get there. James, I think you're taking it right, yeah. Okay, here we go. Solution.
That's what we took.
Which is, it's Newton's second law, but we're going to use the linear momentum equation. So, the forces equals ma plus some of the forces of your outs. We'll do a problem later too, maybe not today, with a helicopter. Line up. Okay? We know it creates a thrust in the back of our mind, but we can figure out using these that there is a thrust. It's generated from that mass flow rate over the velocity. All right, so we only have to worry about the x direction, and this thing isn't moving, so that's garbage. So I'm just going to write this.
Whoa, Wi-Fi network.
And let's write this and we'll talk about
Would
it.
it be V2X and V1X?
Yeah, it will be in the next line.
Oh,
I'm kind of summarizing
everything.
outs and ins, yeah. And let's make, sorry, I forgot, let's make right positive. So, oh, sorry. So let's look at this. So over on the left is all the forces. So we have pressure, 1 times area 1 minus pressure 2 times area 2. All right, and then we have the thrust, this generator, or this reaction force that's holding it there, okay? Equals the mass flow rate 2, because it's going out, and then we labeled that our section 2, times velocity 2. Now, what is the direction of your velocity? To the right?
Right, yeah.
So that's why this is positive, okay? Minus, we have a negative sign here, what's coming in? We have m dot 1 times your velocity 1. And that velocity is going to the right. Okay, so you have to make sure when you do these, you have all the correct signs. All right. Now, what can we cancel something else here?
Yes.
Because that's, we're going to assume atmospheric. And we can then solve for this thrust.
Well, don't you have to bring over V1A1?
Yep, that's what
Okay,
we're
so
doing
that's what
now.
you're doing.
Okay, now what?
Find your MDOTs.
Yeah,
Okay, how?
I don't remember.
Did you say I said the equation?
You did say the equation, what was it?
Row AB,
Rho AV, yep, but,
we don't have the A's, A2.
no, but, what do we know?
We know temperature.
Okay, yep, you guys are on the right path, so if you're,
We need to find the.
we know what? Stuff at 1? Okay, so let's find that.
So you're gonna find it
So you're gonna say find n dot 1, right?
Yes.
Which is rho 1, A1, and V1, right?
Yeah, we can find that one.
Yeah, we can find that,
Yeah.
yeah, sure. How do we find the density?
Well,
You could if it has the right pressure and temperature, right?
correct.
Or you use the ideal gas law, yes. Okay. So, sorry, I'm gonna make another heading, find row 1, you're gonna use the ideal gas. So we can plug that in, right? 78.5 kilopascals times 1,000 pascals and 1 kilopascal. Divided by, do you remember the gas constant value? There?
is it 1?
No? 287? Should ring a bell for some of you. And the temperature is 268. So you will probably not find a table that has that pressure and temperature. So you have to use that gas. Okay, now we can find m dot. 1.02 kilograms per meter cubed times 1 meter squared times 200. Let me know if I scroll up too much. We get 204 kilograms saved.
Now, can't you do the same thing for temperature?
We can't, we don't know the area.
Right, so wouldn't that cancel out then?
What is it?
But we know,
Warmer.
Constant velocity.
Not constant velocity.
No,
density is gonna be the same throughout, right?
No, because the pressure changes.
your control volume. But, and then it's M out.
There we go, conservation of mass. M dot 1 equals M dot 2.
Yeah.
Oh, well.
Yeah. So I was confused where I was going.
Yeah.
That's what I was trying to,
Dragging out the M.1 and M.1.
oh, I skipped one, right? Summation of out equals the summation of n. Because there could be certain circumstances where you have multiple things coming in and going out, right? And then I think we have everything now, right?
Yeah.
So let's plug away. Now, thrust for this reaction force, 204 kilograms per second. I'm going to try putting brackets around my things, see if you like it better. Minus, now I don't know why I did this, I could have brought them together, right? 200 minus gotta convert that to, gauge.
Well, isn't that gonna be negative?
It will be, yep. Then it will add on to that, right?
Right.
And you end up getting 83 or 84 kilonewtons.
Whoops. And that's it.
Yeah. Do we have everything in the equation? I think so. And is our direction right? It is, right?
Yeah.
Otherwise, this would have been a negative and that would have been flipped. Yep. So which way did we have it? To the left or to the right? To the right. So it's a reaction force on that control line, holding it there. So the stuff is shooting out this way, okay? And it kind of basically forces this to go that way, but we need to hold it there kind of thing. Good. Questions? We just did your first thing, momentum analysis. All right. Take a 5-minute break. We'll do one more. Okay? We'll get up, stretch.
Tonight.
Oh crap, it was Tuesday, that's right.
I'm not going.
No. Oh, you hear him?
Joe?
No, God, no.
Did that, no.
That's 16. That's a no-go, mister.
So what do we need to get this presentation? What time you work Wednesday?
5 o'clock.
Maybe that at 4.
I gotta leave here at 4:30.
You get here at 4:30?
Leave here at 4:30.
It's have to be 4:45.
I can't do it today. I can actually do it after 4.
I'm not feeling it today.
Didn't see it.
Take a break. I'm just going to make this sketch. Action.
Eric, make big fingers.
I'm gonna head out.
Yeah, that's fine. Let me know how you feel. You want to use it to make appointments?
No.
I will.
Take something. I was really excited last night.
Where, when I was living in the dorms, I was getting sick, I felt like every month, it was terrible.
Just being around people.
Yeah, just that. But now that I live off campus, I don't think I get sick nearly as much. Thank God.
All right, so we'll do this practice problem. So here is a curve and a hose. And say we wanted to create a force or an anchor to hold it right here. Okay? We want to figure out that reaction force. All right, so water comes in here at this pressure. I don't know if that's gauge pressure. Gauge pressure, yes. So this is gauge pressure. And at 2 meters per second. And the diameter of this is given, so we can figure out all that. Shoots out at atmospheric pressure, or 0 gauge, and at that velocity, and we have the diameter of that. Go ahead and make that sketch. And we'll go right ahead and get right to the solution. Yeah, take your time.
No. Copy paste it.
I could, yeah, no. I need a portable printer. I had a portable printer that fit in my laptop. I wasn't gonna, I wasn't.
In your laptop?
Yeah, don't they make small ones? Oh, not in the laptop.
I was gonna say, in the laptop, what do you want?
In a tree.
They do make them, I assume they're only.
But I wasn't planning on doing this, I was gonna do a different one, but I think this is more applied. The other one has a, oops, it has a cone. You ever see like a flow meter that has a little ball, a steel ball that goes up and down? That was kind of what this problem was, but instead of a ball, it was like a cone shape. It was a little tricky. I should have sketched an inventor to show you the shape. But this one's better.
Is that P1G that's?
Yeah.
P1G, gauge pressure. Yep.
It's a little curve, that P.
Yes, it is.
Oh, like a density?
Yeah. But
It does, actually.
The units didn't match up with it. but-
Yeah. I could have called it Riley.
Yeah,
Right units, right? That's the hardest thing I'm getting fluid students to do is they write out density of the tank. They don't write out rho. Yeah, so I'm not sure where they're getting that from. And that, what is this? I don't know what that little circle is. Right here. Don't worry about that circle. So the control volume's there. I labeled my forces, I labeled my velocities in and out.
So it's kind of like the same problem, like,
I'm gonna do it the same way. Just stuff changes a little bit.
Yeah.
Like velocities are now
definitely,
negative in V2, right?
right, yeah.
And what about the Y direction when you're looking at this? I want to know, if I wanted to hold that up, Is there any water shooting in the Y direction or coming in the Y direction?
Not coming
Not coming in, but going.
but going through.
We're going through, but that's inside the control volume, don't worry about it.
Right.
Going out, it's only in the
X
X direction. So technically, the only reaction force in the Y would be the weight of the water in the tank. That's it. Okay? But if this now shot at an angle, then it would, right?
Yep.
Then you'd have to worry about it. Like a lot of fire hydrants, they have it at an angle, so you have to figure out all the components of it. So continue working, I'll just write, we'll just do everything, we'll just start right with the X direction. So, what's that? Oh, that's all right, I'll go slow.
Oh, no, you're good. I just got sketching it out real quick.
Plus summation of m dot b and the x, so it's no vector equals.
Color you.
What do we do, out first? I always have to remember.
Yep, you do out.
I'm gonna call it O minus dx.
Wait, where did Peach? Oh, never mind.
Then we have, so we did the forces, and then what's coming out? M dot 2 times what? Negative V2? And then coming in, we only have one going out. Minus M dot 1 times what?
D1.
E1. Negative, negative.
What are we trying to find for it?
We're trying to find that reaction force, yep. Bolting force, and then you can then go ahead and size bolts or clamps, right? For machine design. So does everyone understand how you do the control volume? You label all your forces, label your velocities coming in, the states, and how we can write it in our equation. That makes sense? Yeah. Okay. Now, we can cancel P2, right?
Wait.
Let's get the zero gauge. And we can solve for our x.
Can you get rid of that dot 2v2 because now, well, we gotta buy one else to
We can do what? We can assume steady state, conservation, mass, states that m dot 1 equals m dot 2. We can simplify this a little bit like this. The only thing we don't know is what?
V2.
V2.
Well, we don't know the area either.
We know the area, we know the diameter.
Yes, but we don't know area yet.
We can find it, yeah. Okay, so we know P1 and A1, right? We know V1. So is everyone almost caught up? Okay, so let's find what? You want to find MDOT?
Yeah, sure.
So we'll do MDOT 1, so that's density 1, area 1, times what, row AB 1. So density of water is 1 what?
It's 1 kilogram. Oh, it's 1,000.
It would be 1 gram per cc,
Right.
or 1,000 kilograms per meter cube, times area is what? Pi,
R squared.
sure, so 150 divided by 1,000,
Yeah, you just,
pi r squared.
it's supposed to be 0.07. So I got.
Oh, check mine, see if I did it right. 150 over 1,000 squared times
Yeah,
pi,
I just did 115 and then
Yeah.
squared.
Yep. So pi r squared, and the velocity is 2. It's not moving very fast. And can someone put that in their calculator?
What is it?
1,000 times your area times 2.
$300.
300? 300 meters squared? Okay. Seems big. Wait, why is 2.15? Shouldn't it be times that? There.
So you get 141.
141?
Yeah.
Can I second that? There we go. Almost off by 2.
Sorry, I was looking at.
That's all right.
There.
Oh, not meters squared. Kilograms per second. I was thinking area. Is that what you got in?
I got 45.
I got 141.
150 divided by 1,000
Squared.
squared.
Times pi.
Oh, times pi. Okay. Well,
Yep.
that's serious.
Yeah, probably about right.
Yeah.
Okay, so we have, that's equal to MDOT, right? That, we have that, now how do we find V2? You can.
We can do the same equation.
Exactly.
And then just go.
Densities are gone, right? Oh, it's pi r squared, right? Pi's cancel. Just showing you if this ever happens again, this comes out to be this. So R1 was 300 squared divided by 160. Todd ought to check that for me too. They did that.
Should we divide it in millimeter towns?
Don't need to,
Oh, because
because they're gonna cancel anyways.
Don't need to be halved.
Oh, yes and no. Should be what, 150? You're gonna get the same number because they're gonna, it doesn't matter, but R1 was, yeah, 150 and then 80? Yeah, do that. Good call, thank you. Good catch. You would have found out that it wouldn't have mattered. Because if you divide by 2 on each, they're gonna cancel. So, but you do it right. Let's do this.
7.03 meters.
A good check is to what? Realize that the area got smaller, so it should go higher. Just someone check that again, just double check. And then now, we can find this, right? This is, what was it, MDOT first?
Yep.
What's that number, 141 kilograms per second times negative V2?
Yep.
Minus 2 meters per second. And then plus or minus, I think. P1, which is 100 kilopascals times 1,000 times the area. That area is pi 150 divided by 1,000 squared. Now, hopefully it should come out to be negative 8340 or something like that. That's what they have. Comes to negative 9. I'm not Dr. G, I can't do all that in my head. They had 8340? No?
Yeah, 8342, but.
8342?
Yeah.
Yep, that's close enough. What'd you mess up on?
I'm trying to figure it out.
Negative, right? Should be.
Yeah.
Pretty much then our force is then going to the left, not to the right. Pretty close. Good. Cool. I like it when the plan works. Now you know that external force, figure out what kind of clamp, how big the clamp needs to be, or the bolts to hold it. That's all next, you do the strengths and machine design. Okay. So, I will review Thursday. We'll do 2 or 3 more problems. I'll post a new homework now so you can work on that. And then, what did I say? You have a work day. So, Thursday's week 4. We'll do practice problems. And then, second day, I think we'll either have a work day or just 4 problems. Okay? And then week 5, which is next Thursday, we'll probably have a full work day, more problems, and then we'll review. And okay, sounds good.